Welcome to ViewChem, the Chemistry Animations channel. Mechanism of conduction in conducting polymers. In general, many organic polymers are used as electric insulators. For example, polyethylene, PVC, and Teflon. The main reason for the non-conducting nature of organic polymers is due to the absence of conjugation. In saturated chemical structures, all the valence electrons are strongly localized. These electrons do not contribute to the electrical conductivity of the material. But, due to the extensive research work, scientists are able to synthesize conducting polymers. Conducting polymers are broadly classified into two types. These are intrinsically conducting polymers and extrinsically conducting polymers. In the intrinsically conducting polymers, the conduction of electricity is due to the extensive conjugation in the backbone of the polymer. Extrinsically conducting polymers are basically blended polymers. The blends are responsible for conduction. Intrinsically conducting polymers are further classified into two more types. These are conjugated conducting polymers and doped conducting polymers. Extrinsically conducting polymers also classified into two types. These are polymers with conducting elements and polymers with conducting blends. Conjugated conducting polymers contain alternate double bonds. Doped conducting polymers are formed due to the interaction with charge transfer agents, that is, dopants. Polymers with conducting elements contain conducting fibers in the polymers with conducting blends. Conventional non-conducting polymers are blended with conducting polymers. Polyacetylene is the first example of synthetic conducting polymer. Acetylene, on passing over Ziegler-Natta catalyst at room temperature, forms polyacetylene. Ziegler-Natta catalyst. Vapors of acetylene at room temperature. Polyacetylene film, containing a mixture of both cis and trans structures, is formed. Cis form is in copper color, while trans structure, silvery. At lower temperature, that is, around -80 degrees centigrade, cis form exists. Cis form, on heating above 150 degrees centigrade, converts to trans structure. In a conducting polymer, sp2 hybridized carbon chain constitute the backbone for conduction. On each sp2 hybridized carbon, there will be a single electron in the unhybridized pz orbital. The unhybridized pz orbital lies orthogonal to sp2 hybridized orbitals. The delocalization of electrons present in the pz orbitals results in the conduction. sp2 hybridized carbon containing 3 sp2 hybrid orbitals. These 3 sp2 hybrid orbitals lie in the same plane. Unhybridized p orbital, lying orthogonal to sp2 hybrid orbitals, contains an electron. According to band theory, in the case of insulator, between the valence band and the conduction band, the forbidden gap is more. While in the case of semiconductor, the forbidden gap is moderate. In the case of conductors, the forbidden gap is negligible. In conjugated polymers, the forbidden gap can be decreased by introducing charge carriers through doping. This process facilitates conduction in conjugated polymers. The requirements for a conducting polymer for electrical conduction are: the molecule should have a linear backbone. The molecule should have extended conjugation. Charge carriers, that is, either positive holes or electrons, should be introduced by appropriate dopants. The conducting properties of a conjugated polymer can be enhanced by doping with suitable dopants. P-doping, the polymer, which has conjugation in the backbone, when treated with electron-deficient species, that is, Lewis acids, like FeCl3, or iodine vapor, in CCl4, there takes place oxidation, and a positive charge is created in the molecule. Removal of one electron from the pi backbone of a conjugated polymer forms a radical cation, that is, polarin, which, on losing another electron, forms bipolarin. The delocalization of positive charges causes electrical conduction. Polyacetylene is a neutral molecule with extended conjugation. Its conductivity is very low. On doping with suitable dopants, conductivity increases. Polyacetylene, on treatment with iodine in carbon tetrachloride, forms a radical cation, that is, a polarin. Polarin can be a radical cation or radical anion. In this case, polarin is a radical cation. Polarin, on treatment with iodine in carbon tetrachloride, converts to bipolarin. Bipolarin of polyacetylene, in this mechanism, contains two positive charges, that is dication. In soliton, charge delocalization takes place. Further delocalization of charges can be observed. And doping, when Lewis bases, that is, electron-rich species, are treated with polymer, having conjugation, due to reduction of the polymer, negative charge develops. For example, when polyacetylene is treated with sodium naphthalide, negative charge is developed in the polymer. In this mechanism also, the first step is the formation of polarin, and, in the second step, bipolarin is formed. This can be accomplished by dipping the polyacetylene film in the solution of an alkali metal naphthalide, dissolved in tetrahydrofuran, or by an electrochemical method. Actually, by the addition of one electron, polarin, and by the addition of second electron, bipolarin, are formed. In bipolarin, due to the delocalization of the charge, conduction takes place. Polyacetylene is a neutral molecule with extended conjugation. Its conductivity is very low. On doping with suitable dopants, conductivity increases. Polyacetylene, on treatment with sodium naphthalide, forms a radical anion. Polarin can be a radical cation or radical anion. In this case, polarin is a radical anion. On treatment with sodium naphthalide, polarin converts to bipolarin. Bipolarin of polyacetylene, in this mechanism, contains two negative charges, that is, a dianion. Charge delocalization. The mechanism of conduction in doped polyacetylene can be visualized as mechanism of conduction in polyacetylene. In the conventional organic polymers, all the carbon atoms are sp3 hybridized, and do not conduct electricity, owing to the tightly bound sigma electrons. But another class of polymers, called as conducting polymers, have all sp2 hybridized carbon atoms in the polymeric chain. Each sp2 hybridized carbon atom contains one unhybridized p orbital, at orthogonal position to the other sp2 hybridized orbitals. Each unhybridized p orbital, on the sp2 carbon atom, contains one electron, which can be delocalized, and responsible for electrical conduction. These unhybridized p orbitals combine, to form pi bonds, in an alternate manner. Thus, so formed pi bonds, are conjugated. Movement of electrons, in these conjugated orbitals, results in electrical conductivity. The conductivity of doped polyacetylene is more than the undoped molecule. Because doping of polyacetylene creates charge carriers in the molecule. The charge carriers can be either holes, or electrons. Polyacetylene can be either oxidized, or reduced, to introduce charge carriers. The movement of charge carriers towards opposite electrodes is responsible for electrical conduction. P-doping is an oxidative process in which holes are created in the polyacetylene by removing the electrons from the valence band on treating with Lewis acids like iodine or bromine. Mechanism. In the first step, polyacetylene is treated with vapors of iodine at room temperature. As a result, an electron is removed and a radical cation, that is a positive polarin, is formed. Due to the movement of charge carriers, electrical conduction takes place. Electrical conduction takes place in a positive bipolarin also. Positive bipolarin is a Dicot ion. When polyacetylene is treated with sodium naphthalide, that is when polyacetylene is n-doped, reduction takes place. In the process, electrons are added to the conduction band of polyacetylene. As a result, negative polarin and a dianion are formed. Mechanism. Other conducting polymers. Benzene, polyparaphenylene, aniline, polyaniline, pyrrole, polypyrrole, thiophene, polythiophene. Few important applications of conducting polymers. Conducting polymers are used in the preparation of biosensors, artificial nerves, artificial intelligent materials, flat panel displays, flexible panel displays, ion exchange membranes, rechargeable batteries, printed circuit boards, corrosion inhibitors, antistatics. Further, conducting polymers are used to detect the gases and to absorb harmful radiation from electronic devices. Thanks for watching. Please like, subscribe and share.